We're now going to take a look at an important use of implicit differentiation beyond just calculating the derivatives of an implicitly defined equation. Now, this is going to relate specifically to finding derivative formulas for inverse trig functions. So of course it might be useful to do a little bit of a review of what the domains and ranges are of inverse trig functions. Remember that the goal of an inverse trig function is to say that if I was to go ahead and plug in a value into the inverse sine. That means I'm plugging in a value from somewhere, say from -1 to 1. And what I'm looking for when I do this, if I say I did something like the inverse sine of 1 equals something, what that really means is that I'm asking what angle could make the regular sine spit out the answer of 1. And since there are infinitely many answers to this question, it's the case that we're going to have to restrict where this mystery angle can come from. And so what you'll see listed over here in the ranges are the possible answers that are available for inverse functions. And so we have a couple different ranges. This little symbol here that looks like a C with a tick or maybe like an E mark just means that this value has to be one of the values coming out of this interval. So what you'll notice is that the inverse sine function, the inverse tangent, and the inverse cosecant all kind of have similar sorts of range answers. They can all produce values from -π/2 to +π/2. It's just that some of them can include the endpoints, others of them can't, some have to skip over 0 in the middle, but they all kind of start from -π/2 and go to π/2. In the same way, the inverse cosine function, inverse cotangent, and inverse secant all spit out values from 0 to pi. Again, maybe including the endpoints, skipping the endpoints, or having to skip over a value in the middle, which would be π/2. So this is at least loosely what an inverse trig function is designed to do. It's designed to say, if I was using the regular trig function, what angle would I have to plug in to get this specific answer? And the inverse trig is just attempting to spit out that angle for us. So it's important to note that this -1 that we see up here is not an exponent. So this isn't being raised to a negative power. And so it's definitely important to note that if I have something like the inverse sine of x, that is not the same as saying 1 over the sine function. That means that I'm just doing an inverse function. And so sometimes to avoid using that -1, we'll see inverse functions written as stuff like arc sine of x, or as we've seen already, arc tangent of x. We saw that in a section previously. So what we're going to be trying to do is to take these functions here and see if we can find some derivatives for them. So let's go ahead and see how we might be able to do this. So if we want to find the derivative of, say, y equals the inverse sine of x, then we should note that y equaling the inverse sine of x, again, is going to mean that we are going to have the regular sine of y equal to x, right? That's what we're looking for. But again, that angle that we're selecting there has to be from within the range of -π/2 to +π/2, which of course means that on the unit circle, we can only select an angle that would generate points on this half of the unit circle. So that's what we're dealing with. Well, I'm going to go ahead and try to figure out what the derivative of this would actually look like by instead focusing on using implicit differentiation to find the derivative of this alternate form that says sine of y is equal to x. So I'll state here that we use implicit differentiation, and we obtain the following. So I'm going to go ahead and take the derivative of the sine of y and of the other side, which is just x. Now, to do this, I'm going to do the same sort of work that we've been doing in all of the videos previously in this section. I'm going to treat y like it is a unspecified function of x. So I'm not going to see this as sine y. I'm going to see this as sine of a bunch of stuff with x. And so I'm going to use the chain rule over here to calculate the derivative. Because if I have sine of stuff, then the derivative would be cosine of stuff times the derivative of that stuff. On the other side of the equal sign, I just have derivative of x, and so that's going to be 1. And so I can really quickly and easily see here that if I solve for dy dx, my answer is going to just be 1 over the cosine of y. So far I can see that I've actually kind of done it. I found a derivative formula for the inverse sine function. The derivative is 1 over the cosine of y. Well, what we're going to try to do here is to get this entire derivative in terms of the variable x. So I'm going to say here that we want to get this derivative in terms of x. That would just make it a lot easier to use because it would resemble derivatives that we've had in the past, where when I start with a function, I just get a derivative that contains the variable x. All right, so we're going to think about how to actually do this. And there's actually some nice trig identities that we can make use of here to actually complete this task. So I'm going to say, quickly recall that the cosine squared of an angle plus the sine squared of an angle we know should equal 1. Remember, this is our most common and popular trig identity that we have, and it ends up being really useful here because I believe I could easily solve this for the cosine. Notice that this is going to tell me that the cosine squared of y is equal to 1 minus the sine squared of y. And then from here, this obviously tells me that the cosine of y is equal to either positive or negative square root of 1 minus the sine squared of y. So really here I have two different answers, and I can't really plug both of those in. I want to plug in the one answer that actually fits this particular scenario. And so I need to figure out if the cosine of y is going to be positive or negative. But notice here that since the value of y was already told to us to be inside of the range of pi over 2, or negative pi over 2 to pi over 2, that means it's on this portion of the unit circle. And if I consider any point on this portion of the unit circle, and I think about the cosine of these points, that is, I think about their x-coordinates, what can you tell me about all of their x-coordinates? Well, the x-coordinates for all those points would be positive, or at least not negative. They might be 0, maybe at the very bottom or up at the very top. So since y is in this range, we know that the cosine of y is greater than or equal to 0, meaning it can't be negative. And so we can state that the cosine of y is actually just equal to positive square root of 1 minus the sine squared. Okay, so what we can do is we can take this and kind of update our derivative. So we could state that dy dx, which used to be 1 over the cosine of y, could be replaced with 1 over a square root of 1 minus a sine squared of y. And you might be thinking, Kyle, we didn't answer the question, right? Like, the goal was to get this derivative in terms of x, and we certainly haven't done that. In fact, we've made it look more complicated than what it was before. If only, though, there was a way that I could get rid of this sine of y. If only there was a way to get rid of sine of y so I could only, again, have this in terms of x. Wait a minute. Take a look up here. What is the sine of y the same as? We already said that the sine of y was equal to x. And so if I replace sine of y, notice that right now I'm having that sine of y being squared with x being squared, then I would actually have a derivative that is completely in terms of x. And so I have that the derivative of my function, that is, the derivative with respect to x of my inverse sine function, ends up being 1 over the square root of 1 minus x squared. So that's really, really nice, right? I mean, I was able to get all the way down from this messy equation, use implicit differentiation to get to a partial answer, and then take that answer and finish it off into a nice answer with only the variable of x. Now, of course, this is a derivative rule for the inverse sine, but we still have 6 other trig functions left to go, and we'll tackle some of those in the videos to come.